Hi guys, welcome to the Section 4.2 Examples screencast. I want to take you through a few examples to give you some practice in doing the working with StatKey and doing the randomization tests that we're learning about in this section. Now the first one is just a bit of fun. If this doesn't interest you as much, you can think of this in another context, but let's take a look. This is based on Paul the Octopus back in the 2010 World Cup tournament. Paul the Octopus in a German aquarium became famous for correctly predicting the winner in all 8 games it was asked to predict. And the way this went is that 2 containers of food were lowered into Paul's tank, each with a flag of the opposing teams, and he made a selection by choosing which container to eat from. So check out the video on YouTube. So if you want to check that out, you can link here, click here. I actually have it open. So let's see if I can just cut to the chase here.
Meet Paul the Octopus, one of the World Cup's most successful prognosticators. From his tank at the Oberhausen Sea Life Aquarium in Western Germany, he has successfully picked the winner of all of Germany's World Cup matches so far.
Alright, so you can take a look at that. I'm not going to go through the whole video with you now, but take a look if you're interested, or if you're a soccer fan, or vague memories of that from your younger days. Anyway, or ask your parents if they're soccer fans during the 2010 World Cup. So he made selections by choosing which container to eat from. So is this evidence that Paul has psychic powers and can choose correctly more than half the time? So he predicted the winner in all 8 games. So he had 2 choices. So they had presumably a 50-50 chance each time. So let's define our parameters here and then write down what would be the null and alternative hypotheses. So let's let P naught, I'll write it this way, P represent the proportion of all guesses Paul would get correct. You know, that's kind of like in the long run, or kind of how accurate he is. We want to state a hypothesis about that. So our null hypothesis is that P is 1/2. That is, he's just guessing, versus the alternative hypothesis that he's doing better than guessing, so that would be P greater than 1/2. So it's definitely a one-sided alternative. We're not really interested in whether you could do less than 1/2, because if that were the case, it means not just guessing and purposely guessing wrong, although if we were guessing against Germany, I guess that would be a way of staying alive. All right, so that's our setup, a statement about the null or about our parameter, and we want to test that using a randomization test. All right, what is Paul's sample proportion? So we'll write that as P half, and he got 8 out of 8 correctly. Now we want to see how unlikely it is to have an 8 for 8 record if Paul is just randomly guessing. And we can simulate this with a coin, where each coin flip represents a guess between 2 teams, with heads standing for a correct guess and tails for incorrect. So we might ask, why does this method work for assuming the null hypothesis is true? And that's because the null hypothesis, because we hypothesize, we hypothesize P is equal to 0.5, and that's the same that you would get for a coin landing heads 50% of the time. That's what we'd expect just due to chance. So that's why in this case we could use it. If it were, let's say, something where the null hypothesis were 1 out of 6, one could imagine using a die to simulate that. So we're going to flip a coin 8 times and record the proportion of heads as one simulation. Now before we look at the simulation here, I want to invite you to click on the link to the German Euros coin tosser. I figured since it's a German octopus we could use that. So if you click there, it should open you up. Let's see if I can get that. Back to random.org with the coin flipper. So this is usually you could choose the type of coin, but I've already chosen. So let me go ahead and flip. And so what I've got is 1, 2, 3, 4, 5 out of 8 correct. flip again, and we could do that as a class and do 30 or so that we could collect. So I went ahead and took the role of the class and did this 30 times and tallied the results I got. And so here's my small scale simulation. I did 30 replications of 8 coins of 8 euros and counted the number of times the eagle comes up, which is the heads. So possible values for the number of heads out of 8 is from 0 to 8. So here's what's most likely, right? Not surprisingly, 3, 4, 5, which is close to 50%, 4 and 5 especially, but just due to chance, I ended up getting a few more 3s, but what I didn't get was any 7s or 8s, and I didn't get any 0s. So at this point, it looks like 7, even 7, but certainly 8 would be extremely likely to just happen if the octopus was just guessing. So let's go back over here to our sheet. So if we flip a coin 8 times and do it replicate that 1,000 times, what would we get? Well, let me show you how you would do that with StatKey. So I showed you the link before for StatKey. Let's go over the randomization hypothesis test. We're doing a test for a single proportion. Now, as you saw in a little bit with R, we use the R flip function. We don't really have to look for the octopus forecast. I mean, we could, but that's just 8 out of 8. Instead, we could just, all we have to do really is to set the proportion. So that is, we've got a proportion equal to 0.5. We're going to sample 8 times. We could edit the data and specify the number of times correct, right? And then the sample size being 8. So we could do 8 out of 8. And then specify it that way. So what I was getting at was we didn't really need to have a Paul the Octopus there. We could use this for other cases. So this is our original sample, 8 out of 8, right? But we're going to simulate based on the hypothesis that P is 0.5. So we generate, let's say, 10 samples. So we have a few values of P hat that would happen just due to chance, flipping the coin. Now I'm going to reset and do 1,000 of those. So we'll see that only a few times did we get all 8 correct, and we could actually see what proportion of times that is using the right tail. So if we put 1 for the right tail, that would be what we observed in our sample, and we get 0.004. So 4 out of 1,000 times in my simulation were all 8 correct, right? Just due to chance. Now this one was 6 that's showing here. Here, if I click, I get 7. Over here, these are the ones I had 8 out of 8. So very unlikely, all right? 0.004. So let's take a look. What is the p-value for the sample statistic of 1? So I got 0.004 for ours. Now in this simulation, the simulated proportion was 1 on 4 of them. So same as what I got just now. So that would be the 0.004. Just happened to turn out that way, the same as what they got in the example. All right. So we've quantified how unlikely that was to happen. Very, very unlikely. I'd have to ask you to decide what you think about whether the octopus is really deciding or if it just happened to be an extremely lucky octopus, which did meet its demise at some point along the way. But anyway, quick self-quiz. Visualizing a p-value. If a different octopus only got 6 out of 8, for a sample proportion of 0.75, use the randomization distribution above to shade in the simulated samples that are as extreme or more extreme than this sample proportion. How would we calculate the p-value, and would it be more or less than the p-value for Paul the Octopus? So I'll pause and let you think about that. Okay, so hopefully you have done so. So up here, let's make this... we can make it a little bit wider here. For greater than 0.75, what we're talking about is these here and these. Well, that didn't work so well. I have to pick a different color. But anyway, I'm just going to sketch what we have here. Get back to about where I was. So we're going to have these, and these, and this is what we're talking about for calculating the p-value of p hat was 0.75. Will the p-value be more or less than the p-value for Paul the octopus? It would clearly be much more. There are a lot more samples involved. And if you want an estimate, we can look at the one that I just did. And so we wanted greater than 0.75. Okay, so if we click here and we put in 0.75, now we get this highlighted and we get about 0.139, so roughly 0.14 might be a good guess as to about what the p-value would be. That's the proportion at or more extreme in the right-hand tail. Okay. All right, so let's go ahead and take a look at the next one, support for the death penalty. And now all of these are not life science questions, but what I want is for you to have exposure to a number of different kinds of problems and get the hang of working with thinking about randomization tests. So in this case, we have two samples, both of size 1,000. And in 1980 and 2010, are you in favor of the death penalty for a person convicted of murder? It was 0.66 in 1980, 0.64 in 2010, and the question is, does the data provide evidence that the proportion of U.S. citizens favoring the death penalty was higher in 1980 than it was in 2010? Use P1 for the proportion in 80 and P2 for the proportion in 2010. So state the null and alternative hypotheses. So our null is that there is no change, that P1 equals P2. And the alternative is that it was actually higher earlier. So P1 greater than P2. What is the sample statistic? So that would be p hat 1 minus p hat 2. And so that would be 0.66 minus 0.64 or 0.02. So we're wondering if that's far enough away from 0 that we can find support for the alternative hypothesis given a sample of 1,000. So this is a randomization distribution, assuming the null hypothesis is true. And which of the following is closest to the p-value? So think about how you would find that. All right, and then I'm going to address the question. Okay, so the observed test statistic was 0.02. That's the observed statistic value. So we're looking at the proportion here. And this is out of 1,000 simulations that were run. So p hat 1 minus p hat 2 was equal to 0.02. That's how we got here. But then what proportion is this? Well, is it half? No, that would be half the dots. 0.001 would be way out here. 0.05 or 0.020. So that might take some thinking through what you would have to get, but it looks like about 0.20 is what we're looking at here, which is approximately equal to the p-value. But I want to show you that we can do that in StatKey as well. So I'm going to scroll up so I can get the values again. It was 0.66 and 0.64. So let's go over to StatKey. Now what I want is a test for a difference in proportions. Okay. Now we're not going to worry about finding the specific data. What we're going to do is edit data to put it in. So we have 660 out of 1,000, right? It was 0.66, and then 640 out of 1,000 in the later year. Say okay, so this is the original sample with a difference of 0.02. We could simulate 1,000 of these, and we want to see the proportion at or beyond 0.02. So if we pick the right tail and we go to 0.02, we get the value of 0.187, which is certainly closest to the 0.2 that we estimated based on the picture. All right, to get 0.05, sorry, I did that backward. I put in the value to see, we would have had to be out here around 0.035, and that's what 5% would look like. So hopefully that's helpful to sort of calibrate your eye on that. Again, going back to, well, let's leave it at that. I don't want to confuse there. All right, now let's take a look at example 3. That's sleep or caffeine from memory. So here's an experiment in which students were given words to memorize, and I've seen this showing up in the reading. Then were randomly assigned to take a 90-minute nap or take a caffeine pill. Always nice to be randomized to take a nap. They were then tested on their recall ability. We test to see if the sample proportion, if the sample provides evidence there's a difference in mean number of words people can recall depending on whether they take a nap or have some caffeine. And what's the strategy to do, I suppose, before an exam? So the hypotheses are mu sleep equals mu caffeine versus mu sleep not equal to mu caffeine. So the question is just whether there's a difference, which is a two-sided hypothesis. We're not sure, is it better to have sleep or better to have some caffeine? So the sample statistic, based on what was actually observed, is that the sleep group got more correct than the caffeine group by 3 on average. So here's our statistic. And so we're going to use the randomization distribution to state the p-value. So indeed the p-value is right here. It's that probability of being greater. Oh wait, now we have a two-sided test. So our p-value is going to be twice 0.022. So we're taking the direction in the right-hand tail at or beyond and doubling that. And now I'm ignoring the two tail. I would have preferred checking the right tail and looking at that in that direction, because this is where observed value was. It was positive. So we're looking at the probability at or beyond, and then we're just doubling that value. Turns out to be the same as if you just add these two the way StatQ set it up. But I think intuitively I prefer for you to think about taking one tail and then doubling it when you have a two-tail test. Okay. Now the last is a self-quiz. So p-values from a randomization distribution. Now we're not given a lot of information here. We're just testing mu equals 50 versus mu less than 50. We don't know the context, but the sample data is x bar equals 43.7. So first it asks, where will the randomization distribution be centered and why? What kind of test, and how can we find the p-value once we have the randomization distribution? So think about that one, give it a try, and put your answer in. That is, make an estimate or give an answer. So where will the randomization distribution be centered? Well, think about the octopus thing. It was centered wherever the null hypothesis specified. When it was a difference in means, it's centered at 0 because we're assuming the difference in means is 0. So here it's centered at 50. And that's because we imposed the null hypothesis. Okay. So 50 is the null hypothesis. So we assume we assume H naught is true when we do a randomization test. All right, is this a left tail, a right tail, or a two-tail test? Well, this is a left tail test because our alternative is less than. So how can we find the p-value once we have the randomization distribution? Well, we calculate or find, I guess. We want to find the proportion of randomization statistics less than or equal which 43.7 or 50, so it's less than or equal to the observed or original sample. So we want to see how extreme the sample statistic of 43.7 is in the left tail of the randomization distribution and calculate that. So in this case, if I were to sketch it, it would be centered at 50, and somewhere out here, we're not sure where because we don't know the sample size or anything else, but that would be 43.7 out here somewhere. 43.7. Sorry, not the p-value, but the test statistic, and the p-value would be this tail area down here. All right. So hopefully that helps. That's how we would find the p-value. We would find the proportion at or below that value. So thanks for listening. Be sure to practice these and let me know if you run into any problems. Take care, and we'll see you on the next one.